Hello everyone. This lecture pertains to acid-base homeostasis. Please note that there will be a brief quiz following this lecture. In this short lecture, I will be giving you introductory information on acid-base regulation. I will be answering questions like, why do disturbances in acid-base balance occur? And how do we classify these disturbances? In particular, I'll be detailing the differences between metabolic acidosis and alkalosis, and respiratory acidosis and alkalosis. And then finally, I'll be focusing on the question, what compensatory mechanisms are in place within your body to help rectify these disturbances, altering pH values and bringing them back into normal range? Homeostasis of pH is tightly controlled. pH values of the extracellular fluid are about 7.4, and in the blood, the pH ranges between 7.35 and 7.45. If blood pH becomes less than 6.8 or more than 8.0, it can be very detrimental for an organism, many times leading to death. Acidosis or acidemia is a term used when values are below 7.35. Alkalosis, alkalemia, occurs when values are above 7.45. Here is a review of the previous slide. Again, homeostasis of pH is tightly controlled. Extracellular fluid is 7.4, and the pH of blood ranges between 7.35 and 7.45. Survival range of blood pH is between 6.8 and 8.0. And the term acidemia describes the state of low blood pH, while acidosis is used to describe the processes leading to this state. Furthermore, alkalemia refers to the state of high blood pH, while alkalosis is used to describe the processes leading to this state. Now let's focus on the question, why do disturbances in acid-base balance occur? Here is a table from your textbook detailing some of the causes of acid-base imbalance. The upper portion of this table describes how gains in hydrogen ion concentration occur. Number 1 pertains to the generation of hydrogen ions from an accumulation of CO2 in the body caused by hypoventilation. Number 2 states that proton concentration can increase due to the production of non-volatile acids from the metabolism of protein and other organic molecules, like an accumulation of lactic acid after an intense workout, or ketoacidosis, a serious complication of diabetes mellitus. Number 3 states that hydrogen ion concentration can increase with diarrhea. Diarrhea actually causes a substantial loss in bicarbonate, which again is one of the most important buffers for maintaining acid-base balance in the blood. With the loss of bicarbonate ions from the body, free proton levels tend to rise in the blood. And number 4, gain of hydrogen ions in the blood can occur due to the loss of bicarbonate in the urine. One other source of hydrogen ion gain, which isn't on this list, number 5, is a gain of hydrogen ions due to ingestion of acid by drinking acidic drinks like orange juice, which is high in citric acid, sodas, coffees, and many other acidic foods and drinks. The bottom part of this table details some of the sources or causes leading to a loss of hydrogen ions. The first is utilization of hydrogen ions in the metabolism of various organic anions. Number 2 is the loss of hydrogen ions with vomiting after eating a meal, particularly after parietal cells have delivered an enormous amount of hydrochloric acid into the lumen of the stomach and bicarbonate into the blood. Number 3 is a loss of hydrogen ions in the urine. And number 4, hyperventilation, which tends to lower the partial pressure of carbon dioxide in the blood, leading to respiratory alkalosis. So, to sum up, starting from the top of this slide, anytime there is an accumulation of acids in the body or a loss of bases, there will be an increase in the concentration of hydrogen ions, which will cause the pH to drop and acidosis to occur. Starting from the bottom of the slide, Anytime there is a substantial loss of acids or an accumulation of bases, there will be a decrease in the concentration of hydrogen ions, leading to a rise in pH and alkalosis. So why is pH control important? Most enzymes function only within a narrow range. Acid-base balance can also affect the transport of other electrolytes like sodium, potassium, and chloride. And pH can also affect the action of other regulatory molecules like hormones. Now I'd like to focus on the question, how do we classify these acid-base disturbances? Let's first zero in on number one, on the cause of the disturbance. First, the term metabolic or respiratory are giving you information about the cause of the acid-base imbalance. Metabolic refers to the biochemical processes involved in the body's normal functioning. In this case, the term metabolic is telling you that the cause of the acid-base disturbance has to do with a malfunction of those normal biochemical processes. Respiratory is referring to the fact that there is a respiratory system disorder that is the cause of the acid-base imbalance. In regards to the effect of the disturbance, number two, again, as we've already discussed, acidosis is a term used when blood pH falls below 7.35, and alkalosis occurs when blood pH is above 7.45. Number three, compensation, is your body's response to the acid-base imbalance. Compensation refers to how your body responds to acidosis or alkalosis. Now, to put this all in perspective, remember, the first line of defense against a shift in blood pH are your chemical buffers, which include mainly your bicarbonate buffer system, and to a lesser extent, phosphate and protein buffer systems. The previous slide talked about compensation or compensatory mechanisms, which refers to the second line of defense against a shift in pH. There are both respiratory mechanisms and renal mechanisms in place that also play a role in returning blood pH back to its normal range. Buffers function almost instantaneously, while respiratory mechanisms take several minutes to hours. The renal mechanisms take the longest. Renal mechanisms may take several hours to days, but are the most effective in returning blood pH back to its normal range. This slide is one of the most important slides in this lecture. It's going to help you provide a diagnosis for patients with an acid-base disorder. First of all, note whether the pH is low, which would indicate acidosis, or high, which would indicate alkalosis. Then, decide which value, either the bicarbonate ion concentration or the partial pressure of carbon dioxide, is outside the normal range and could be the cause of the problem. If the cause is a substantial change in bicarbonate ion concentration, then the problem is metabolic. If the cause is due to a change in the partial pressure of carbon dioxide, then the acid-base disturbance is caused by a respiratory issue. And finally, look at the value that doesn't seem to correspond with the observed pH change. If it's inside the normal range, then there is no compensation occurring. If it's outside the normal range, then the body is partially compensating for the problem. Normal bicarbonate ion concentration in the blood is around 24 milliequivalents per liter, and the partial pressure of carbon dioxide is usually around 40 millimeters of mercury. So now, let's check your understanding of the information given in the previous slide. Here is a short case study. A patient is in intensive care because he suffered a severe myocardial infarction or heart attack 3 days ago. The lab reports the following values from an arterial blood sample. Blood pH is 7.3. The bicarbonate ion concentration is 20 milliequivalents per liter. And the partial pressure of carbon dioxide is 32 millimeters of mercury. What is your diagnosis in regards to this acid-base disturbance? If you said metabolic acidosis with respiratory compensation, you'd be right. A buildup of lactic acid as a result of a heart attack or heart failure can lead to metabolic acidosis. So how does your body control proton and bicarbonate concentration in the blood? It does so by both renal and respiratory compensatory mechanisms. Let's look at the renal compensation first. With renal compensation, the kidneys can eliminate large amounts of acid and can also excrete base like bicarbonate ions. They can also conserve and produce new bicarbonate ions. In fact, the kidneys are the most effective regulators of blood pH. If the kidneys fail, pH balance fails. What nephron structures participate in this process? If you remember from the renal section, hydrogen ions are secreted and bicarbonate ions are reabsorbed all along the nephron in the proximal tubule, thick ascending limb, distal tubule, and collecting duct. Let's start with renal responses to acidosis. Sufficient hydrogen ions are secreted to reabsorb all of the filtered bicarbonate ions inside the nephron. Hydrogen ions that are secreted will react with filtered bicarbonate ions, be converted to carbon dioxide, and then reabsorbed back into the body. Still more hydrogen ions are secreted, and this process contributes new bicarbonate ions to the plasma, as these hydrogen ions are excreted bound to non-bicarbonate urinary buffers, such as hydrogen phosphate. Tubular glutamine metabolism and ammonium ion excretion are enhanced, which also contributes new bicarbonate ions to the plasma. In summary, again, these are the renal responses to acidosis. Number 1, sufficient hydrogen ions are secreted to reabsorb all the filtered bicarbonate ions inside the nephron. Number 2, still more hydrogen ions are secreted, and this contributes new bicarbonate ions to the plasma, as these hydrogen ions are excreted bound to non-bicarbonate urinary buffers, such as hydrogen phosphate. Number 3, tubular glutamine metabolism and ammonium ion excretion are enhanced, which also contributes new bicarbonate ions to the plasma. The net result is that more new bicarbonate ions than usual are added to the blood, and plasma bicarbonate is increased, thereby compensating for the acidosis. The urine is highly acidic and can have a pH value as low as 4.4. Let's switch gears now and discuss renal responses to alkalosis. In this case, the rate of hydrogen ion secretion is inadequate to reabsorb all of the filtered bicarbonate in the nephron, so significant amounts of bicarbonate ions are excreted in the urine and eliminated from the body. Also, there is little or no excretion of hydrogen ions on non-bicarbonate urinary buffers like hydrogen phosphate. With alkalosis, tubular glutamine metabolism and ammonium ion excretion are decreased so that little or no new bicarbonate is contributed to the plasma from this source. In summary, here are the responses to alkalosis. Number 1, the rate of hydrogen ion secretion is inadequate to reabsorb all of the filtered bicarbonate in the nephron, so significant amounts of bicarbonate are excreted in the urine and eliminated from the body. And in addition, there is little or no excretion of hydrogen ions on non-bicarbonate urinary buffers, like hydrogen phosphate. Number 2, tubular glutamine metabolism and ammonium excretion are decreased so that little or no new bicarbonate ions are contributed to the plasma from this source. The net result is that plasma bicarbonate concentration is decreased, thereby compensating for the alkalosis. The urine is alkaline, as high as greater than a pH of 7.4. Now let's turn our attention away from renal compensatory mechanisms and concentrate on respiratory compensations that are activated during an acid-base disturbance. As we've already discussed in the respiratory section, peripheral chemoreceptors in the carotid bodies and the aortic arch respond to changes in arterial blood. These chemoreceptors detect decreased levels of oxygen caused by hypoxia, but are much more sensitive to increased hydrogen ion concentration caused by metabolic acidosis and increased carbon dioxide levels. With acidosis, these chemoreceptors will send a signal to the medulla in the brainstem, which will activate mechanisms that increase ventilation rate. On the opposite end of the spectrum, with alkalosis, increases in arterial blood pH and decreases in the levels of carbon dioxide depress respiratory centers. The resulting alveolar hypoventilation tends to elevate the partial pressure of carbon dioxide and restore arterial blood pH towards normal. The pulmonary response to metabolic alkalosis is generally less predictable than the response to metabolic acidosis. In order to pull everything together, the Davenport diagram is a useful graph that summarizes and expands upon many of the physiological concepts in this lecture related to acid-base disorders. The Davenport diagram is a nomogram that predicts the different disturbances in acid-base balance based on the blood pH and the amount of bicarbonate in solution. Acidosis will shift the curve to the left, and alkalosis will shift it to the right. As illustrated in the next slide, since respiratory disturbances will shift the amount of bicarbonate in solution in the same direction as levels of carbon dioxide, then respiratory acidosis will be in the top left and respiratory alkalosis will be in the lower right-hand corner of the nomogram. Before we get started, I want you all to notice the partial pressure of carbon dioxide in this graph. There are 3 lines that represent different partial pressures of carbon dioxide. The changes in the partial pressure of carbon dioxide are caused by either respiratory acidosis or alkalosis as expected. With respiratory acidosis, pH levels tend to fall and bicarbonate ion concentrations become slightly elevated. With respiratory alkalosis, pH levels rise and bicarbonate levels drop slightly. With metabolic acidosis and alkalosis, there is no change in the partial pressure of carbon dioxide, which stays fairly steady at 40 millimeters of mercury. But there are huge changes in bicarbonate ion concentrations and pH levels. Here's a Davenport diagram detailing the changes that occur with both metabolic and respiratory acidosis and alkalosis. The X in the center indicates normal parameters for any organism. This concludes the lecture on acid-base regulation. Please don't forget to take the quiz immediately afterwards while the information is still fresh in your mind.